All right, guys. So let's. I want to take probably the first about. Hey, guys, let's get ready to learn. So I want to take about the first 15 or 20 minutes going over this lab and going over the work and power worksheet, because today we are going to be doing a lab on work and power. You're going to have some work and power math problems to work on today after the lab. Then we're going to have a quiz next class. The quiz next class is going to be on energy. So it's going to be the law of conservation of energy. It's going to be on kinetic and potential energies, particularly the math part of it, and it's going to be on work and power. So we got a lot of stuff we have to do today. So what you needed to do last class for this, it was more of a math-based lab where you didn't necessarily need to physically do anything. However, you needed to mentally do things. So what came of this was you were to pick 3 different sized masses from the mass kit. I'm assuming you all kind of picked different ones. I'm going to go through the math here. Follow along with how I do the math compared to actually what my numbers are, just because I'm going to pick 3 different masses here. I'm going to use the 1,000 gram, I'm going to use the 500 gram, and I'm going to use the 200 gram. All right? So what that means is this. One thing to understand is that you must use kilograms when you're dealing with these formulas. So if mass 1, it's going to work here for me. What's going on here? There we go. So mass 1 was 1,000 grams. Mass 2 was 500 grams. Mass 3 was 200 grams. So you guys should know by now, how do we convert grams to kilograms? Move the decimal place which direction? How many times? 3. Just the same as dividing by 1,000. So therefore, the mass is 1 kilogram, 1 kilogram, 1 kilogram. 0.5, 0.5, 0.5, 0.2, 0.2, 0.2. The first part up here, section 1, was just you calculating what the gravitational potential energy was of these 3 different masses in 3 different positions. So, the 3 positions were on the floor, on the desk, on top of a group member's head. So therefore, the height on the floor is 0. The desk measures to be about 0.76 meters. Group members, I'm just going to make up a number. I'm going to say 1.8 meters. Yours will be different depending on how tall your partner was. So that's going to be the same for all of the trials here. Now, potential energy, guys. All of this is following this formula: mass times g times height. That should technically be a lowercase g. What's g always? Gravity. What's the magic number? 10. 9.8 or 10. So depending on what you used, you may get slightly, I'm going to say, off answers, because ultimately what you should get if you did the math correctly was that your potential energy at the top of its fall should be equal to the kinetic energy at the bottom of its fall. So if you didn't get that in your math, you didn't do the math correctly. So let me show you what I'm talking about here. So potential energy of an object with 0 height is going to be 0. So I'm going to go right through and throw those in there, because if height is 0, anything times 0 is going to be 0. Potential energy of the object, or the 1 kilogram mass on top of the table, well, the mass is 1, so it's going to be 1 times 9.8 times its height, which is 0.76. That comes out to be, nope, I didn't do that right on the calculator. 1 times 9.8 times 0.76 comes out to be about 7.45. Did someone say what, as if they don't know how I got that? All right, next one. It's going to be mass times gravity times height. So again, it's going to be 1 times whatever. So we're going to just jump straight to the 1 times 9.8 times 1.8, which is the height. And it comes out to be 17.64. All right. So again, now, once you can do one of them, guys, you can really do all of them. It's the same formula over and over again. So now we're going to have to do 0.5 times 9.8 times 0.76, about 3.72 is the potential energy of that mass from that height. And then 0.5 times 9.8 times 1.8 is 8.82. And then finally, the last bit here, we're down now to a 0.2 mass. So 0.2 times 9.8 times 0.76 comes out to be about 1.49. And then the last potential energy here, 0.2 times 9.8 times 1.8 comes out to be about 3.53. So any questions, guys, with calculating the potential energy? It's really just plug and chug, plugging what's given to you into the formula and getting the potential energies. Any questions on how to do that? So what are you noticing? Which scenario has the greatest potential energy? Yeah, the one with the most mass and the most height, which makes sense. All right. All right, so I should actually write those down. So 0, 7.45, 17.64. You're on tape here. You're on digital recording here if you need to ask me a question.
Ms. Barron wants to know what room you're in, A5.
This room. All right. Next section. This is where, when I was walking around helping kids last class, where the greatest amount of confusion was. I think a lot of people forgot how to use this formula right here. All right. I even said when we were going over this, you don't need to use a stopwatch to figure out the time an object takes to fall. We've been dealing with this formula for the whole entire year, and it's not going away anytime soon. So now the second part was calculating what the kinetic energy was of these. So therefore, the mass of object 1 was 1 kilogram. Distance dropped. Well, we're going to copy that from above. Time it takes to fall. This is where you're going to use d equals 1/2 gt squared. All right? So if it's falling from a 0 height, time it's going to take to fall is 0, which means 0 velocity, 0 kinetic energy, and 0 potential energy. As far as 0.76 goes, if an object is falling from 0.76 meters, we're going to use the d equals 1/2 gt squared. I think a lot of people forgot how to use this. 0.76 is going to equal 4.9 t squared. What do we have to do with 4.9? Please tell me the right answer. Don't say subtract. Thank you. Fantastic. Divide it out. So 0.76 divided by 4.9 is equal to 0.76 divided by 4.9. Comes out to be 0.31. Take the square root of 0.31. It's 0.76 because of the height, the distance dropped. So the d is 0.76. Nope, I'm figuring out the time it takes to fall. So when you do that, it comes out to be about 0.39. All right, and then as far as the 1.8, how long does it take to fall? We're going to put 1.8 in here. So 1.8 divided by 4.9, and then we have to take the square root of that, because that would be about 0.5. Let's see. Clear. It's going to be square root of 0.37. About 0.61, about. All right. So questions on how to calculate the time it takes to fall. All right. Velocity. This formula is back. V equals gt. So all we're going to do is multiply these numbers by, if you use 10 for g, multiply it by 10. If you use 9.8, there goes my middle school voice again. If you use 9.8, use 9.8. Keep that consistent. So I used 9.8. So the velocity is about 3.82. And then 0.61 times 9.8 comes out to be about 5.98. Any questions on how to figure out the velocity? Fantastic. So potential energy, where did we get this from? Up above. You already figured it out. All right. So I copy these down here. So you have 7.45. I have 17.64. Now, ultimately, guys, what you are comparing is the potential energy from the top of the drop to the kinetic energy at the bottom of the drop. I said it before. I'm going to say it again. You'd know if you did your math right if they are equal. So as far as the kinetic energy goes, it's 1/2 mv squared. What must you do in this formula first? What do you have to do first? Order of operations. What do you have to do first? Square root? I don't see a square root in there. Square. well, technically, we have to square it first. All right. So therefore, we have to v squared, 3.82 squared, is going to be about 14.6. Now we must times it by the mass, which was 1. I'm not even going to bother doing that. And then we have to multiply it by 1/2. You can multiply it by 0.5 or divide by 2. And it comes out to be about 7.3. It's a bit off due to rounding, but you notice how very close these are. If we try to figure out the kinetic energy for the 1.8 meter height, the velocity was about 5.98. So we're going to square that first. Then we are going to multiply that by the mass, which is 1, and then times it by 0.5. And we get about 17.8. And you notice how very close those are. Due to rounding, they're a bit off. But so any questions, guys, with solving for potential and kinetic energy? So I'm not going to go through and do weight 2 and weight 3. It's the same formulas, same setup. You know if you did the math correctly, if you got the potential energy is just about equal to the kinetic energy, which makes sense. Because when you did the roller coaster simulation at the beginning of this energy unit, where there was the energy meters, and it said total energy was always at 100%. When you had a high kinetic energy, what did you have for potential energy? Very, very low. But whatever it was, these two added up equaled the total energy. So therefore, when kinetic energy went down, what happened to the potential energy? Went up. When potential energy went down, kinetic went up. All right, it's inverse. So I'm gonna jump right to the analysis questions. Your graphs, if you did the graphs correctly, which I think most people did because I went around and helped people, your graphs should have pretty much crisscrossed like that, meaning when potential energy was really high, kinetic energy was really low, and then as potential fell, kinetic rose. All right? And let's look at the analysis here. So when was the potential energy the highest in the experiment and why? Give me a scenario. When was the potential energy the highest? Matt, Brian, you already gave me this answer before, so why don't you give it to me again? What's that? Yeah, exactly. When it has the most mass and height, that's when the potential is going to be the highest. Good. 2, when the kinetic energy, when was the kinetic energy the highest in this experiment and why? When was it? Yeah, again, it's going to be at the bottom of the fall from the highest point with the highest mass. If potential was the highest up there, as it falls, it's losing potential and gaining kinetic. So at the bottom of that fall, the kinetic energy is going to be very high. 3, in theory, the potential energy at the top of the drop should match the kinetic energy at the bottom of the drop for each trial. All of the potential energy transferred to kinetic energy in your test. Yeah, it should. It definitely should. Does this mean that you lost or gained any energy? You didn't lose or gain. Because remember, guys, the law of conservation of energy says energy is not created or destroyed, it just changes forms. So there you go. That's how we use the law of conservation of energy to explain. Was this experiment perfect? No. Because as you saw above, I got like 0.1 at most, or like 0.09, 9/100ths of a decimal off. It's because of rounding. So rounding was definitely a human error. 5, which has a greater effect on kinetic energy of an object, mass or velocity? This was a good question. A lot of kids were debating this question. So let's look at the formula first. So we know that it's 1/2 mv squared. So which one do you think is going to have the greatest change? I heard some mass, I heard some velocity. Which one, guys, if you plug a number into this formula, if you plug a number in for mass, you plug a number in for velocity, which one's going to have the greatest change? Velocity, yeah. Because velocity is squared. So wherever the velocity is, you're squaring that. So velocity has the greatest effect on kinetic energy. 6, would the golf ball have more or less potential energy on the moon than it does on Earth? Why? Ooh, this is a good question. So let's look up here. We know that potential energy is equal to mass times gravity times height. What's gravity on Earth? 10 or 9.8. Is it the same on the moon? No. Is it greater or lesser on the moon? It's less. Less gravity. That's why when you see pictures or videos of people walking on the moon, they kind of float around. Gravity's a lot less. So therefore, if this number is smaller, potential energy is smaller. All right, so potential energy is smaller on the moon. Yes? Can you change gravity on Earth? Yeah, I mean, yes, absolutely. Yeah, that's a good question. Question is, can you change gravity on Earth? Yeah. So if you ever hear like on a plane will get up to, like a fighter plane, up to like 3 or 4 Gs. That's changing gravity on Earth. 1 G is equal to 9.8 meters per second squared. So if you are then going down very quickly, you are changing, even on a roller coaster. A roller coaster can reach 3 or 4 Gs on a free fall. Yes, you are changing gravity on Earth. Good question. 7, you guys did this up here. Your potential energy and kinetic energy, as one goes up, the other goes down. And then the total energy, well, it's going to be up here. So that's going to be your third line right at the top. That's going to be the maximum for both. All right? So what I wanted you to get out of this was seeing that when you do the actual calculations, we're putting numbers to the theory that we've been doing. Energy does not get lost. It changes forms. So potential energy at the top of the fall is equal to the kinetic energy at the bottom of the fall. Okay? So any questions on this lab? All right, let's look at the next next bit here. So I told you guys that consider the front page of this as your notes for work and power. I'm not giving you notes. I'm not doing a PowerPoint presentation. These are your notes, and they're good notes. They give you the formulas. They give you the definitions. They give you the units of measurement. If you took time, I told you to take about 10 minutes, 15 minutes reviewing the front of the page, then you could do the back. All right, so let's look at the back here. First, let's write down these formulas on the chalkboard. We have work equals force times distance, and what's power equal to? Force divided by time? Work divided by time. Good. All right, so some of this stuff should look familiar. Again, it's just a little bit of review, looking at units of measurement. So for force, newtons. For work or energy, joules. For mechanical advantage, we haven't done that yet. So I'm going to skip over that, but due to knocking out ones, you can figure out what's left. Small p stands for what? Small p? Nope. Momentum. P equals mv, that's momentum. So momentum is kilograms meters per second. D is distance, that's meters. Big P stands for power, which is measured in watts. Therefore, mechanical advantage has no units of measurement. If we move over to here, energy, we want to match the definition. Energy is what? What did you guys put for energy? Look at your homeworks. What did you put? C. What about for power? Well, let's go down to joules. What's joules? B. Good. Work? So questions with the top sections. Oh, I do I? Yeah, I do. Yes, power uses, or work uses energy. Work is A. I have 2 going to C. You're right, I listened to a wrong answer and just went with it. Yes. It's clear as mud, right? Let's do it again. Let me erase those. I can do that. All right, joules. We know that joules is the units for energy and work. Joules is B. All right. Look at the front of your paper. What is the definition of work? A force applied for a distance. Good. So therefore, it's going to be which one? Yeah, so which one is it? A. Good. Power? D? Fantastic. And energy? C. There we go. Clean it up a little bit. Very good. This section, this is a good section. It really makes you think what work is. Work is force times distance. So if you did not exert a force on an object or you did not move at a distance, you didn't do work. So I could push against this chalkboard as hard as I want, and I can sweat, and my muscles couldn't get tired, but by definition, if I didn't move it, I didn't do any work. All right? So if we look at these, we want to know more or less for the same amount of work. You use more force to move an object. More work. Good. You lift a 20 Newton object faster. Is there anything dealing with time in this formula? No. So you're doing the same amount of work. You raise an object a shorter height. Yeah, less work. Good. You move a lighter object. Does this have anything to do with mass? Same. You move an object farther. You're changing distance, you're increasing it, so it's more. Okay? Let's look over here. Is the person doing work? When pushing a 1,000 Newton car 20 meters, are they doing work? Yes. When lifting a rock off the ground? Yes, they're moving at a distance. When holding a book in their hand? No. There's no movement, no distance. When pushing hard against a brick wall? No, not moving at a distance. When walking up the stairs? Yes, absolutely. Good. Fantastic. Let's move to this section here. More or less power. An engine can lift an object faster. Yeah, more. So when we're working with power equals work divided by time. So if we can move it faster, the T is going to be a smaller number, which means we have more power. Someone takes more time to push a car. It's going to be less power. Yeah, so if I'm standing next to Hulk Hogan pushing a car, I'm obviously going to push it faster than him because I'm exerting more power. Yeah. No laughs, no smiles? No like, ah, what a loser? No? All right. Must have been a late Thursday night for you guys, or I'm not funny. You take the same amount of time to do more work. So same amount of time to do more work, so this increases, so therefore it's going to be more. And finally, same distance, same time, more force. There it is. All right. So questions on the non-math related stuff. Okay, let's move on to some of the math problems. So I will do 2 from each side. Just due to lack of time, I want to get you guys going on your lab. So this side, so let's do this one. You move a 25 Newton object 5 meters. How much work did you do? So if we're talking about work, it's force times distance. We have a force of 25 newtons, a distance of 5. Oop, my bad. Force is 25. How much work did you do? 25 equals 5W. How much work did you do? 5. 5 joules. Let's do the next one. You carry a 20 Newton bag of dog food up a 6-meter flight of stairs. How much work did you do? Work equals force times distance. The force. Yes.
Is this work equals force times speed?
Yes. If there's nothing between them, it's multiplication. Yes. My bad. What did I do? Man, I sure did. Yep, sure is. So therefore, work equals 25 times 25. Yeah, I just like to make a mess out of things, apparently. Yeah, no kidding. I'm botching everything today. So next one, you can carry a 20 Newton bag of dog food up 6-meter flight of stairs. How much work was done? We have a force of 20. We have a distance of 6. 20 times 6 is what? 120 joules. Okay? So again, super simple formula. There's 3 different variables. What's given to you, plug it in, and plug and chug. All right? Yes. But we're not dealing with any angles here. We're assuming for this one, when you press in the steps, your leg is pushing straight up. Okay. All right, if we are looking for power here, car uses 2,500 joules in 25 seconds. Find the power. How much work was done? 2,500. Time is 25. What are we looking at here? 2,500 divided by 25? There we go. So 100 watts of power was done. Last one I'm going to do here, a 60-watt light bulb runs for 5 seconds. How much energy does it use? So power equals work divided by time. Watts is power, so we have 60 equals energy, so it's going to be work. What's it going to be? Fantastic. All right. So if you did not complete these guys, give them a whirl. All right. So any questions that I can answer for these? All right, let me explain the lab.